All right, today we're going on a bit of a detective mission. We're going to uncover the hidden forces that decide the state of, well, everything, from the water you drink to the very air you're breathing right now. I mean, have you ever really stopped to think about that? It's a question we bump into every single day. You can pour a glass of water, but oxygen is just all around us, totally invisible. They're both just molecules, so what gives? Why isn't everything just, solid or all gas? So here's the twist. The secret isn't locked away inside a water molecule or an oxygen molecule. No, the real action, the important part of the story, is happening in the empty space between them. We're talking about something called intermolecular forces, and today we are going to crack the code. Okay, so every good investigation starts by surveying the scene, right? And for us, that means getting a handle in the three main states of matter: solids, liquids, and gases. Let's break it down. In a gas, molecules are basically strangers at a huge empty party. They're super far apart and could care less about each other. In liquids, things get a little cozier. It's more like a crowded concert. Everyone's close, but you can still kind of squeeze past each other. But solids, they're totally locked in, arm in arm, just vibrating on the spot. So this immediately makes you ask, what is this invisible glue that's holding liquids and solids together? To figure that out, we need clues. We need evidence. And our first big break comes from a single, very interesting family on the periodic table, the halogens. Let's see what they have to tell us. Okay, take a look here. All of these are like chemical cousins. They're all related. But watch what happens as we go down the list. The molar mass, which is just a fancy way of saying how heavy and big the molecule is, goes way up. And now look at the states at room temperature. We go from gas to another gas, and then, boom, a liquid, and finally, a solid. That connection is just impossible to ignore. So what does this tell us? It's pretty clear that as these molecules get bigger and heavier, some kind of stickiness between them gets stronger. It starts grabbing onto its neighbors, pulling them from a free-for-all gas into a liquid, and then squeezing them even tighter into a solid. So, what is this force? So, our halogen clue is leading us to a pretty solid theory. It seems like there's a direct connection between how big a molecule is and how strong these forces are between them. So let's put a name to this force. This stickiness we're seeing, it's mostly because of something called dispersion forces. Now I know it sounds super technical, but the basic idea is actually kind of simple. Electrons are always zipping around inside a molecule, right? Well, just for a split second, you might get more of them on one side. That creates a tiny temporary magnet, and that little magnet can pull on a neighbor. And here's the really crucial part. These forces exist between all molecules, everything. And this right here just lays out the logic perfectly. As we saw with our halogens, bigger molecules have more electrons zipping around. More electrons means a better chance of creating those little temporary magnets, which makes the dispersion forces stronger. And stronger forces, well, that just means more stickiness. It's a perfect cause and effect chain. And that's it. That's our first huge conclusion. When you're comparing similar types of molecules, size matters a lot. Bigger means stronger attractions. This one simple rule explains everything we saw with the halogens, why big old iodine is a solid while its tiny cousin fluorine is a gas. But hey, one piece of evidence is never enough to close a case, right? We need to be sure. So let's test our theory using a completely different measurement: boiling points. Think about what you're actually doing when you boil something. You're just adding energy, heat, to literally break those forces apart. You're trying to overcome that molecular stickiness so the molecules can fly off and become a gas. So it totally makes sense. The stickier the molecules are, the more energy, and therefore the higher the temperature you're going to need to boil them. And wow, this chart just makes our case perfectly. It's basically a picture of how strong these forces are. I mean, look at water, way up there at 100 degrees Celsius. Then look all the way down at acetaldehyde, which boils at just over 20 degrees. This chart is practically yelling at us that the forces holding water together are way, way stronger. So here's the real punchline. It takes a ton of energy to pull water molecules apart. But for acetaldehyde, it takes almost nothing. And get this, a normal room temperature of 25 degrees Celsius is already hotter than its boiling point. That's why it's a gas in your house. The forces holding it together are just too weak to even bother keeping it a liquid. And you know what? This works in reverse too with freezing. To get molecules to lock up into a solid, you've got to suck energy out. If their natural attraction is weak, you have to get them super cold to force them to stick. And that means a really low freezing point. Once again, the data confirms it. Water freezes at a much higher temperature than ethyl alcohol, just proving again how incredibly strong its intermolecular forces really are. So, after looking at all the evidence, from the size of molecules to their boiling points, I think we're finally ready to deliver the verdict. What is the single most important factor that determines if something is a solid, a liquid, or a gas? It's the strength of its intermolecular forces. That's it. Full stop. That is the master rule that governs our physical world. So let's recap the investigation. We started with our big clue from the halogens, linking a molecule size to its state. We tested that idea using boiling and freezing points as a direct way to measure that stickiness. And it all led us to one simple verdict. It all comes down to the strength of those invisible little forces between molecules. And now we can finally go back and answer our very first question with total confidence. Why is water a liquid and oxygen a gas? Because the forces between water molecules are incredibly strong, holding them together. And the forces between oxygen molecules, they're super weak, letting them just fly free. Mystery solved. Isn't that wild to think about? These tiny, completely invisible attractions are literally responsible for building the world we see and touch every day. It really makes you wonder, what other huge hidden rules are out there, just waiting for us to find the right clues? Thanks for digging into this with us.